Today I will describe quantum electrodynamics. I will describe its Lagrangian and the symmetries. Quantum electrodynamics is the theory, the quantum field theory that describes interactions between photons and electrons. And it's sort of the first quantum field theory that was really well developed and also was very successful, of course, in confirming all kinds of data about the interactions between electrons and photons. So the photon, I didn't describe yet the photon field. I talked about quantum fields for spin 0 and spin 1/2 particles. The photon is a spin 1 field. And as you probably all know, the photon, the field corresponding to the photon is the electromagnetic potential. So it is actually the Maxwell field A mu, which combines the vector potential and the scalar electric potential. And the electric and magnetic fields, E and B, they can be expressed in terms of these potentials in the usual way, and I'll write them down in a covariant notation. I think well, most of you must have seen those. The way they are usually written is that E can be written as a time derivative of A minus the gradient of the potential, and this is the rotation of the potential. If I now introduce a field strength, F mu nu, in such a way that F0I is the electric field and Fij contains the magnetic field, then these equations together can be written as F mu nu equals d mu A nu minus d nu A mu. So this is called the field strength. And contains both the electric and magnetic fields. And then the Maxwell equations, which gives you the electric charge density and the other Maxwell equation in terms of the current. So we have charge density and a charge current density. These are the Maxwell equations. They can be written in terms of the field strength in the covariant notations, and the Maxwell equation then becomes d mu F nu equals J nu E, where this denotes the electric current. Charge, current. And there's an important fact that you can read off from these Maxwell equations, namely F mu nu is a tensor, it's called, because it has two indices, and it's antisymmetric. So from here we derive directly that if I take another derivative, that d nu of the left-hand side that must be equal to 0, simply because actually there's an anti-symmetrization in these two indices, and the derivatives can be exchanged. So this is equal to 0, and this implies that also the current on the right-hand side always has to be conserved. And of course we know that fact, that electric charge is conserved, but this is an important requirement, that the current that we couple to the electromagnetic field must be a conserved current. Now this is the field equation for the photon field, and just like the other fields that I described, this field equation can be derived from a Lagrangian. So I get the Lagrangian for actually the field A mu and the Lagrangian from which these field equations can be derived is, and I'll use this normalization, so it's a Lagrangian expressed in terms of A mu. It's again quadratic. So if I vary this Lagrangian with respect to A mu and satisfy, and in order to derive the equations of motion, you find that the Euler-Lagrange equations indeed give you this part of the equation. But then we also want to introduce the coupling to the electric current, and this can be done by adding a term of the form A mu J mu E. So there's a source, a current that couples to the A nu field, and this coupling must be such that indeed the current that I write down here is conserved because, well, as I'll explain a little later, there's an important property that this Lagrangian has, namely that there's a gauge invariance under, well, gauge transformations of the electromagnetic field. Before I do that, let me explain how you obtain currents, electric currents, that are conserved. Actually, there's a very important fact about Lagrangian field theory. As I said, symmetries are much more manifest in Lagrangian field theory, and one of the consequences of this is that we can derive from a Lagrangian formulation of the some field theory the fact that if you have a symmetry, then corresponding to that symmetry there must be a conserved current, which is known as Noether's theorem. So the electric charge current will be a particular example of that, and since that's the case where I'm interested in, let me explain Noether's theorem and its derivation in an example which gives you an electric current. So Noether's theorem Noether's theorem is the statement that corresponding to a symmetry in the Lagrangian, we always have a conserved current. And I'll describe an example, and the example I'll start from will be the Lagrangian for a charged particle, a spinless particle. If a particle is charged, then the field that we have to use to describe it must be a complex field. And for a charged particle, the Lagrangian looks like this. So that's for a charged spinless particle like the pion, the pi plus and pi minus particles. Then there's a symmetry that I can change phi to some complex rotation of phi, and then of course phi star goes to e to the minus I chi phi star. This is a symmetry since you can check directly that these two will cancel from the Lagrangian. This is a symmetry only if chi indeed is a constant, not really a function of the coordinates. But in order to derive the Noether current, actually, it's convenient to indeed make this parameter dependent on space and time. So if I take chi to be some function of space and time, then of course this Lagrangian will no longer be invariant, because then in here you find that the derivatives can act on this function. And this is, well, a way to derive actually the Noether current. Let me write down these transformations first in infinitesimal form. Infinitesimally, I can write down phi goes to phi plus delta phi, where delta phi is I chi times the same field phi, and of course delta phi star is minus I chi phi star. So there are two variations of the fields that I can now take my Lagrangian and vary. Then you find that actually what I will do is actually vary not just the Lagrangian, I'll vary the action. If I take these variations of the fields and plug them into the action, you find that the variation of the action S, the action is the integral of the Lagrangian, so I find an integral. And then the only terms that survive are actually the terms where indeed the derivative acts on the function chi, because if the derivative doesn't act on chi, then you'll find that these two variations of phi star and phi will cancel out, basically because of the fact that we already noted that if chi is a constant, then indeed these transformations are a symmetry of the Lagrangian. So it's only when the derivatives act on the parameter chi that we find a non-zero contribution. And then the variation of the action becomes d mu chi of actually, which is multiplied then by an expression which basically comes only from this term in the Lagrangian. Since we actually took one of the derivatives that act on chi, it's only one of the other derivatives that still remain in the expression. So I'll find phi star d mu phi minus phi d mu phi star. And there may be that's actually the expression that you get up to a factor of I actually. And from this actually, if I know that this variation of the action can be written like this, then I can conclude now that since I have the classical field equations derived from the fact that the variation of an action should be zero, then if the classical field equations are satisfied, then this expression should be zero. And since chi is an arbitrary function, you find actually that the expression which I have here, and I'll call that actually my current, J mu E, which if I introduce an additional constant in front of it actually, which is the electric charge. So this expression has to satisfy the conservation law, because this is zero, and so by partial integration this d mu can be put on this whole expression, and therefore the d mu of J mu E must be zero if the field equations are satisfied. And this is directly derived from the fact that I know that the variation of the action vanishes when the field equations are satisfied. So this is an example of a Noether current associated now with the symmetry of complex rotations in the Lagrangian. There's actually another example which will be more relevant actually for quantum electrodynamics. So instead of having a scalar field, electrons are described but have spin 1/2, so they must be described by Dirac Lagrangian. So what I'll do next is just simply indeed write down the Dirac Lagrangian, which looks like this. And this Lagrangian has, similarly as the Lagrangian over here, a symmetry under rotations of complex rotations of the field psi, and therefore you can also derive a Noether current, which is the current d mu. There was a question here? Okay. D mu the electric current associated with the Dirac field, actually because in here there's only one derivative, the current will actually be an expression without any derivative, because if I do the derivation of the Noether current with this parameter chi, then you indeed get a similar expression as here, d mu chi times an expression that involves the fields without any derivatives. So the Noether current will be psi bar. There's the electric current of electric charge in front of it, psi bar gamma mu psi. So this is a conserved current, and now the Lagrangian for electrodynamics is quantum electrodynamics is simply obtained by taking the Lagrangian for the A mu field with indeed a coupling to the current, together with this Lagrangian for the complex Dirac field, and then you identify the current which is in here with the current that's the conserved current derived from this Lagrangian. So J mu E is exactly this expression. So if you then add these two Lagrangians together, so the Lagrangian for the A field and for the Dirac field psi, then you obtain the Lagrangian for quantum electrodynamics. So let me write down then those two terms together. I'll actually use a notation that in terms of F mu mu, which is d mu A mu minus d mu A mu, so that I can write down the Lagrangian in a simpler and shorthand notation. The Lagrangian for QED is minus a quarter F mu squared plus psi bar. Then there is an I gamma mu d mu minus m acting on psi. And here I've introduced a notation d mu, which is not the ordinary derivative. D mu contains the ordinary derivative, but it also combines precisely this coupling which I have here, in terms of the electric potential A nu times this expression psi bar gamma mu psi. And then you notice actually that if I write this out, I can write it in the form, this term, psi bar A mu gamma mu psi. That it looks very similar to the term which I have here in the to make it even more obvious, I'll write it like this: A mu, gamma mu, A mu, in between psi and bar and psi. Then you notice that it looks like precisely the kinetic term which I have here. And so what I've done is just added A mu to the definition of my derivative. So if I take the covariant derivative as being d mu minus IE A mu, then putting this expression in here, you'll find that there's an additional term in here contained, which is precisely the coupling of the electromagnetic current of potential to the electric current of the electrons and positrons. This is called the covariant derivative. And the reason why it's called the covariant derivative is actually related to this symmetry which I showed you exists for the Lagrangian. This symmetry is still now present here in the Lagrangian, and even better actually, the symmetry is now a symmetry. This symmetry under rotations, complex rotations, will be a symmetry even if we have a function chi which is dependent on space and time. So there's a gauge invariance, which I think is the most important property of this Lagrangian. There's a symmetry under psi going to e to the I chi times psi. And if we simultaneously shift a mu by a mu plus 1 over e d mu chi. So chi is a function now of space and time. So if I do this transformation, I transform the electric potential together with the field, then you can check that the Lagrangian is invariant. And so there are two terms here in the Lagrangian that have to be verified. First of all, f mu, and this you can read off from its definition. If we do this transformation, you'll find that in here, f mu goes to, there's an additional term that you get because of this change in a mu, and I'll write down the additional term, which is d mu on d mu chi minus then the other term which you get is d mu chi. And since again the derivatives can just be interchanged in order, this change is equal to 0. So indeed f mu doesn't change if I add a derivative to my vector potential. The more tricky term is in here, where if I do now this rotation, then because chi depends on space and time, the derivative which is in here can act on chi. And so I have to verify indeed that that doesn't affect the Lagrangian. Well, this can be verified explicitly. I'll do that here. If you take the expression d mu minus I a, this covariant derivative acting on psi, and so what I'll now do is make my transformation, this transformation, so you'll get d mu minus I e a mu plus 1 over e d mu chi, and now acting on e to the I chi times psi. Now I notice here, first of all, that the 1 over e and e cancel out, and also the derivative can now act on this e to the chi. And so what I'll get from here actually is that there's an additional term. So what I want to do actually is now take this function, this exponential in front of the derivative. So I'm going to take this through, and then the derivative will change from d mu, and then there's the additional term plus I d mu chi, which comes from the fact that this derivative has acted on the function here in the exponent. But then I have this change also in a mu, which is minus e a mu, and then I drop the factor e in here, so I get minus I d mu chi acting on psi. And now you notice that indeed these two terms cancel. So the fact that the derivative acted on the function chi and a mu is shifted by this parameter gives you a cancellation, because precisely those two terms cancel each other. So what I end up with is that this is transformed into this expression, which is then equal to e to the I chi times the original expression or shortly d mu psi will, under the gauge transformation, transform into e to the I chi d mu psi. So a gauge transformation simply multiplies this with the same phase vector that the function psi was multiplied with. And now if you take this transformation and then notice that, of course, psi bar is rotated by the the complex phase. So if I add the transformation that psi bar goes to psi bar e to the minus I chi, then again this will cancel the e to the plus I chi, which you get from this transformation. The only thing you have to check now indeed is that the e to the I chi, which multiplies psi, can be taken through to the other side and then cancel the other phase. And that's precisely what the covariant derivative is designed to do, that this expression can just simply be that indeed such a phase vector can be taken through if you simultaneously transform the gauge potential. So this is a symmetry of the gauge symmetry of this Lagrangian, and the significance is that the gauge field A mu, well, I call it now a gauge field because it gauges this symmetry, has fewer physical degrees of freedom than just the 4 components that you would normally think this field would have. This is a 4-component vector field, but the independent components of the photon, there are only 2 independent components of a photon. A photon has 2 polarization states, well, helicity +1 and helicity -1. Those 2 degrees of freedom of the photon should actually be contained in this field A mu, and the fact that we have here a 4-component field tells us that we have a redundancy in the way that we describing the photon. The photon field must have actually described a particle with 2 polarization states, and this fact is accounted for in the because we have this gauge invariance. Furthermore, the gauge invariance can only work if we have a Lagrangian like this without any mass term. And so also the gauge invariance ensures that the photon remains a massless field. So gauge fields are always massless fields as long as you, well, don't work. Well, I'll describe a little later how you make massive gauge fields, but at this moment we only have a gauge invariance if we also have a massless field. So you cannot write down a mass term for the photon field without destroying the gauge invariance. So let me now come to, well, the Feynman rules for quantum electrodynamics. I think I now explained the basic, most important properties of the Lagrangian, and so we're going to do now a sample Feynman diagram calculation in quantum electrodynamics. I'll actually make the situation a little more general. Here I've written down simply one Dirac field which couples to the electromagnetic field. Of course, there are more particles in nature that carry electric charge, and so the full Lagrangian must, of course, contain terms which describe other particles as well. So if I have, for example, an electron and a muon fields which both couple to the electromagnetic field, I need to write down 2 Dirac spinners in my Lagrangian, one for the electric field, or for the electron, and one for the muon. And so then, of course, the mass, which I write here, in this case is the electron mass, but you can also write down an expression like this, where I write down a Lagrangian which contains, describes the muon, and then you write down here the muon mass. Okay, the rules, the Feynman rules, which I described yesterday, actually were obtained from just looking at the Lagrangian and then applying a set of rules where you look at, first of all, at the quadratic part of the Lagrangian, which tells you what the propagators look like, and then finally you look at the interaction term, which tells you what the vertices look like. So the Feynman rules are like this. So the Feynman rules for QED, well, we have 2 kinds of particles, the photon and the electron, and each of them we should write down a propagator. And the propagator for the photon, for the electron is written down with a straight line like this, continuous line like this, with an arrow actually, and the arrow indicates the fact that we are dealing with a charged field, so we have to tell us which direction the charge current is going. So this is also the way that we can distinguish in Feynman diagrams between electrons and positrons, because for a positron we have to draw the arrow in the other direction. And then for such a propagator which has a certain momentum p associated with it, we write down an expression in the Feynman rules which is the following. This is actually the inverse of the kinetic operator in the Lagrangian. And similarly for the photon, we'd like to do that actually and write down, look at the quadratic term in the Lagrangian and then invert that and write down the propagator. Actually there's a problem there, and that has to do with the fact that there's this gauge invariance. Because of the gauge invariant, the kinetic term for the photon won't be invertible. So there's a way that we have to fix that by modifying the Lagrangian in a very precise way so that we can indeed write down a propagator which is invertible. And the way to do it is actually to fix a gauge, because if we have such a gauge invariance, then we can actually choose a gauge for the photon field. And the usual gauge that is chosen has to do with the condition that we want the gauge field to satisfy an equation like this. This is the only way that we don't break Lorentz invariance. But the way we do it actually is not by imposing this condition. Actually what we'll do, and this, to really explain how, why this can be done would take too long. What you actually do is we add a term to the Lagrangian that's needed to fix this gauge, and the gauge fixing term, so we have to add something here, is a term that involves precisely this condition and some arbitrary parameter that we can choose at some point. There's a parameter which I'll call psi, which multiplies this condition, the square of this condition, and I'll add this term to the Lagrangian in such a way, and actually what you can show is that because of the gauge invariance, it doesn't matter if I derive now the Feynman rules using this Lagrangian, then eventually this parameter psi should drop out from my final answer. And I can actually use that to fix, choose a particular parameter psi which is convenient. Well, with this choice of gauge fixing term, the propagator for photon, so for the photon I'll use a notation like this with a wiggly line. The photon doesn't carry any charge, so I won't have to point an arrow, put an arrow on this, but it does carry a momentum q. And the photon propagator, which I'll give a name delta, it has actually two indices because the photon field has one index and the propagator actually connects one part of the photon field to another part, and it's related actually to the 2-point, to the way that a photon could propagate from here to here, and then I have to specify which polarization states I am propagating. And actually what you find out is that the photon propagator isn't exactly diagonal, but can be made diagonal in such a way that the same polarization state that is at one point will become the polarization state that we get at the other side of things. So the photon propagator has two indices, mu and nu. It's a function of q. And with that choice of gauge fixing term, the photon propagator is minus I. And again, I have something that has to be written as with the numerator and the denominator. In the numerator I have a mu metric plus then a term that involves this parameter psi, q mu divided by q squared. And then here we have one over q squared plus I epsilon. The fact that there's no m squared in here is of course because the photon is a massless field. And here I have two terms, a mu and this additional term which depends on psi. And you can see right away that there's a convenient choice for psi, namely if I put psi equal to 1, this term will drop out. And actually for certain Feynman diagram calculations this is convenient to do. Although it's also convenient sometimes to keep this parameter in your calculations because, as I said, the parameter should finally drop out from the whole expression. But this is then a check on your calculation that you didn't make any errors, that if you keep this parameter in and then do the whole calculation of the Feynman rules, then you should verify that in the final expression psi drops out. But if I now take psi to be 1, then this whole expression simplifies to minus I a mu divided by q squared plus I epsilon. So these are the two propagators. Finally, I also have an interaction term, a vertex that comes from the interaction term. And here actually I wrote down already the interaction term. So the interaction term comes actually from this part in the Lagrangian where we have the photon field coupled to the electron field. And since the electron field is a charged object, you find actually that there's always an incoming and an outgoing electron at a vertex. So the only vertex, so what we had here were the propagators. And so we have two kinds of propagators, and there's only one vertex in QED, which combines one photon with two electron lines. And I'll write it like this. I have two electron lines and one photon line coming together. And there's a momentum P and momentum P prime here. And at this vertex we always should have momentum conservation, so the momentum of the photon is the difference between P and P prime. And in the Feynman rules, a vertex gets a very simple contribution. It can be read off actually from the interaction term, and maybe I should go here in order to verify that I get the right normalization. In the interaction term we wrote down the photon field and psi bar and psi, and it also contains the coupling, which is actually the electric charge for the electron. So we find that at the vertices we have to write down this the combination of this electric charge together with the coupling that we have here, which also involves a gamma matrix. So there is a mu index associated with the vertex because the photon had a mu index. And so we find that at the vertices we have to write down a factor, which is I times E, the electric charge, times the gamma matrix, the Dirac gamma matrix. And this is all that you have to write down at your vertices. And then this gamma mu index, as I said, gives you, the mu index gives you the polarization index for the photon. And if the photon happens to be a photon which is an internal photon, say like the one which we have here in the propagator, then this mu index and that mu index must be the same, which in the expression means that you have to contract this mu index with the mu index in here. So let me now come to a sample calculation, a Feynman diagram calculation using these rules, and see how they give you an answer. Actually, this sample calculation will also illustrate a little bit more about the Feynman rules, because these are the rules that describe the propagators and the vertices. But in a Feynman diagram, we also have external lines where you have to write down expressions describing the wave functions for the external particles. Yeah. So the process that I will consider will be a simple experiment where we take E plus and E minus, and we want to know the amplitude for E plus and E minus to produce, say, a muon pair, mu plus and mu minus. So what happens actually is that the positron and the electron annihilate, and the way they can annihilate is giving they give a photon, and the photon then decays and produces the muon pair. So the Feynman diagram for this will be a diagram of this sort, where you have indeed the incoming electron and positron pair, and then the photon is being produced, and then the muon lines, which are the outgoing particles, are indicated in a similar way as the electron over here. And in here, the Feynman diagram must be completed by writing down also the wave functions for the external states. And those wave functions are the spinors u of, say, P1, where if P1 is the momentum of this electron, and for the positron, I have a wave function which is also some spinor v as a function of P2. I wrote down the expressions for these spinors in the first lecture, and those are the expressions that you have to associate with the wave functions of these incoming states. And similarly, the outgoing muon will have polarization or a wave function associated with it, and those are some function v of k1 and u bar of, sorry, that must be k2 and k1. So if I now write down the Feynman rules and write down the expression over there, you get an amplitude which is the following expression. I hope it fits on here. Yeah. It's an amplitude which depends actually on the indices. Say if I write down indices A and B prime in here, so this amplitude has a lot of indices, A, B, A prime, B prime, which are the indices associated with these spinors. Then just to indicate that these wave functions actually need not be the same wave function. I indicated it with the same symbol, but you have to be careful, of course, that I can choose another wave function for the outgoing state than for the incoming state. And actually, if you're not worried about precisely which state we have to have in here, then in the final expression I can have to sum over the outgoing wave functions. And so there must be some way in which I can parameterize this by this index A. So the propagator of the amplitude is also a function, of course, of the two incoming momenta, P1 and P2, and of the two outgoing momenta, K1 and K2. And the expression we have is, well, we have two vertices, so I'll write down an expression for each of the two vertices, and then I'll also include the propagator. And so for the first vertex, we have we have I, E, then we have to write down the spinor for P1. Oh, sorry, yeah, it's P2. Yeah. Then there's the gamma matrix, gamma mu, which is in between those two wave functions. So this is the first vertex. Then I write down the propagator. And then I have a similar expression for the second vertex. So I, E, and then the momentum for the wave function for the outgoing states, UA prime of K1, and again the vertex function gamma nu. So notice that I have the mu index and the nu index here being contracted with the same indices of the photon propagator. So eventually there are no indices that are left over. And then finally I have here the wave function for the other muon state. So I have now included all of those wave functions in here, the four polarization of the wave functions for the external legs. I have two vertices which I've introduced and the photon propagator. And then this is the amplitude. And well, I already explained yesterday, if you have an amplitude like this, then the thing you want to compute is not really the amplitude itself. You want to compute transition probabilities. And probabilities should be written in terms of squares of amplitudes. And actually this will make even the calculation a little bit easier. If we write down the transition probability, I call it dW, then this is equal to, well, actually what I'm going to do is actually take the square of the amplitude, but if I'm not interested in the polarization or the precise polarization of the electrons and muons, I'm going to sum over the initial polarizations, and I'm going to average also over the final polarizations which I have over here. And so the expression is going to be normalized with 1/4 because I'm taking the average of the polarization. Then, well, it's actually the other way around. I'll have to take the average for the initial polarizations and to sum over all final states. So the average for the initial ones gives you 1/4. And then I sum over all of these polarizations, A prime, B prime, and A and B. Then I'll take the square of the amplitude. And then there's the momenta Pi and Ki. And this must be squared and summed over. And actually I have to multiply this with the phase space factor, which is the integral over my external, the final momenta. Well, I wrote down that part of the calculation yesterday. What I will do is actually show to you how to compute this square. At least I show you what the result is of this. If you compute the square and sum over the polarizations in here. So I have to take this expression, plug it in here, and compute the square. And then you find that the result can be written in the following way. This expression, dW, can be written as, well, there are squares of the expressions in here, and you notice that in here I had two vertices, so twice a factor of the electric charge. So in the square I get 4 times the electric charge, so I get 4 e to the 4th. Then I have in here q squared, actually q must be equal to the sum of these two momenta. So I have an incoming momentum P2 and an incoming momentum P1. So Q is equal to P1 plus P2. And the square of Q, P1 plus P2 squared, that's actually the center of mass energy squared of these two states. And that's actually called usually denoted by S, which is called a Mandelstam, one of the Mandelstam variables. So from the propagator in here, I get a 1 over S for each amplitude. And since I take the square of the amplitude, I get 1 over S squared. And then the rest I have to do is actually evaluate this expression with the wave functions in here and the gamma matrices. And I can write this symbolically first as in the following way. I'll introduce a symbol L mu, which is a function of P1 and P2, which is going to describe this part of the diagram. And then there's a similar function for the other part of the diagram, which I'll call L mu K1 and K2. For this function, L mu P1, P2 is the sum, actually 1/4 of the sum of A and B over A and B of I'll first write it down and then explain where it comes from. So it has a sum over the polarizations A and B, which enter in here, like this is A and this is B, and these are the complex conjugates of the same expression. So in here you actually recognize that you have to sum over these wave functions together with their complex conjugates, and these sums can be computed. I think I wrote down an expression yesterday of the form that UA star indeed can be written in terms of gamma matrices. And if this is a function of P, then you will get P mu gamma mu plus M as the outcome of this sum. And it's these kind of ways that you can now, these kind of expressions that you can now use to evaluate this. And if you do that, then this actually can be computed and gives you a rather simple answer in terms of the momenta. You get P1, P2, mu, P nu, and the other way around, so symmetrized, plus eta mu, P1 dot P2 plus M squared. So there are certain identities that you have to use in order to perform these sums. I think those identities you can find in any textbook, and actually this is one of those identities. For V, you have a similar identity actually, and putting those in, and then you can evaluate actually the trace over the gamma matrices and obtain this expression. Well, make a long story short, I can now plug this back into here, and then you find that dW can be written as 4e squared times, well, there's 1 over s squared, and then there are two other terms which I write as t squared plus u squared, where t and u are two other Mandelstam variables. T is equal to p1 minus k1 squared. So that's actually the invariant mass of energy, which you can construct out of k1 and P1. So instead of having the invariant energy in this direction, you'll take the invariant energy in that direction. So S and T are two variables you can associate with a certain direction in your Feynman diagram. S is associated with this line, but there's also an invariant energy associated with that line. Actually, it's the energy that's being transferred if you have diagrams like scattering processes. Anyhow, U is a similar expression where you cross the last two lines to exchange K1 and K2, and so it's equal to P1 minus K2 squared. Well, this is an expression that's very simple, and so it has a very simple momentum dependence, this transition probability, and this is something you can measure also in experiments, and the fact that, sorry, it's e to the fourth, by the way. Yeah. I exchanged the 2 and 4 here, I think so. It's 2 times e to the fourth, which you have here. So actually there's a normalization in here, which is the electric charge, and this process actually can now be used to actually measure the electric charge in your laboratory. So if you have do this experiment, look at the production of muons through annihilations of electrons and positrons. You can look at the cross-section or at the transition probability, and then you find this behavior as a function of the momenta. And then there's the prefactor, something that you can calculate or at least derive from your experiment, and that's a way to measure the value of the electric charge in your experiments. And actually what I'll do tomorrow is actually look at loop corrections to this process, and then we'll find that precisely indeed the value of this electric charge will depend on where, at what energy we'll do the experiment. So this expression is sort of the first tree-level result, which we're going to correct tomorrow and look at the loop corrections. And then you'll find that this the amplitudes for this process indeed will start depending on the energy of the initial particles. So this is where I'll end today. Thank you. Any questions at this point? No questions so far. Okay, well, see you tomorrow then.